So I'm on page 4 of part 4 of the PDF lecture notes, and I want to now tell you how this model works for combining information across the studies. There's been a lot of genuinely new ideas for you in terms of the details of carrying out the Bayesian paradigm in this course so far. This is probably the first genuinely new scientific idea that we've covered in the whole class. And models like this have a profound effect on contemporary practice. So we're going to spend at least, certainly more than just this afternoon, a big chunk of next time also understanding how these models work. And I have good reason to believe that they also have substantial relevance to applied work here in the Valley and the work that other people are doing here in pharma and other realms. So,
if we have 6 different studies that were run under different characteristics. If all 6 of those were to run under the same, by the same person under the same regime, but would I have to go through what we're going to do now?
The naive pooling idea turns out to be a special case of what I'm about to show you now, in which a particular thing that usually is not 0 turns out to be exactly 0. In effect, that particular thing is the between-study variance in the population that we're trying to generalize to. And so the throw it all into one bucket analysis, which has another name, and I should have put that in the notes before. It's called a fixed effects analysis, whereas what we're doing now is called random effects analysis. So let me get that into these notes. Naive pooling, fixed effects analysis is a special case of the thing we're about to do now, which is called random effects. And the best way to approach uncertainty about that sort of thing, from a Bayesian point of view, since the fixed effect story is a special case of the more general thing we're going to look at, it's always better in the Bayesian world to fit the more general model and then look and see if there is support within the general model for the specialization that leads you to the simpler model. In this case here, what we would do is fit the general model and then look, and then look at and see what the evidence is in the posterior for how big that between studies variability is. And if the posterior is showing you that that variability is close to 0, then maybe it's okay to do the naive pooling thing. So this model is hierarchical at 3 levels. Usually, Bayesian models, the simplest ones we've used so far, are hierarchical at 2 levels. There's the bottom level for the data and the top level for the prior. And the thing that makes this model new for us is there's an intermediate level that I need to describe to you. So let's talk about the data layer first, the bottom level in the hierarchy. It says, remember, yi is the observed difference, placebo minus control, placebo minus aspirin, in the mortality rate in percentage point terms in study I. So now we're going to try to tell a story about before we ever saw those data values, how we think they would behave. And the bottom level of the data tries to do that thing that I've mentioned to you before. It says that study I has something that we'll call a kind of true underlying effect for studies very much like study I. That's this thing called theta I. That's the mean. And if we knew what theta I was, the yi's would be independently normal draws from independent draws from normal distributions with different means, one for each y sub I, and also different variances v sub I. And I've mentioned to you several times now that that's the kind of thing we always want to try to do scientifically. Back in the Bernoulli case study with the heart attack patients, the AMI patients at the Dominican hospital, we want to write down a model that says everybody has their own propensity to die. Yi given theta I are independently Bernoulli theta I, but then we ended up with too many parameters, right? Because there's one parameter for each person and you can't fit that model. So the bottom layer of this data does that same thing, and it looks like it's not going to be fittable because we have 6 theta i's and 6 y sub i's. It looks like it isn't going to work. But the basic idea is that if you were to repeat the exact treatment protocol and patient cohort story for study number 3, for example, and do that over and over again and average all those results together across many repetitions, that number would be theta 3. It would be the truth about the basic story about how to get data with the treatment protocol plus patient cohort story for study 3. So each study has its own underlying theta sub I, and if you knew it, the y sub i's would be independently normal draws with mean theta I. And we are going to take those variances VI as known, because what they are, you remember what they are, is they're simply the squares of those standard errors of the y sub i's we calculated before. Remember I did that calculation with that thing about Pythagoras and so on. So the VI's, to be really careful about it, we should take the VI's and let them be unknown as well. But look back here. Each of the numbers, each of those VI's is a number that's based upon the comparison of two means, each of which has hundreds, in some cases thousands of draws in each mean. And so the actual level of sampling uncertainty that would be present in those V sub i's with sample sizes at the study level, how many patients at the study level we have, would be negligibly small. And so we're going to pretend that these numbers here, V sub I, these numbers are the square root of the V sub i's, and to get the V sub i's, I'm going to square them. We're going to pretend that those numbers V sub i's are known. That makes the bottom layer of the model a little simpler, and it's not that bad a thing to assume because we have so much data in each study. Now, we can't fit. Yes, please. Could I do what? Ah, okay. So the graphical model for this? Yes, I can. Actually, I'm going to do that after I finish explaining the model in algebraic form. Even with the VI's known, we cannot fit the model that's based only on the bottom layer here because we have too many thetas. So the middle layer of the model, which has never been present before in our work, is a layer in which we try to talk about the thetas. And so now, theta sub I represents the so-called true effect of aspirin in the environment in which study I was conducted. If we had some study level predictor variables, if we had some covariates or predictor variables or features, whatever you want to call them, at the study level, this would be a moment where we would want to build a little regression model in which we predict the theta i's from those x's that were measured at the study level. But despite lots of efforts to do so, no one has ever been able to track down important study level covariates in this meta-analysis. We don't know why those 6 studies differed. In particular, even today, no one knows. After a lot of effort trying to figure it out, no one knows why that Amos study was so different from the other one. So we don't have any study level covariates. And so the best thing we can say is that the theta i's should be similar to each other because after all, they're measuring the same basic thing, the effect of aspirin on mortality for people with a heart attack. In other words, as Bayesians, our uncertainty about the theta i's before we saw the y i's, our uncertainty about them is exchangeable. Think about it. Before I showed you the data and I just told you there were 6 studies of the same phenomenon, you wouldn't have known ahead of time which one would get which particular theta value, and especially before I showed you any of the y's. And so before you saw any data, your uncertainty about the theta i's is exchangeable. And the simplest way to operationalize the judgment of exchangeability in the Bayesian story, as we've seen repeatedly, is to regard the exchangeable things as like IID draws from the same distribution. That makes them similar in a particular way. It does not make them identical because they're allowed to vary randomly as draws from that distribution, but it makes them similar. Remember how that worked with De Finetti's theorem? The yi's, which were binary outcomes in the mortality case study, were all judged to be exchangeable by us. And that judgment implied that yi given theta became IID Bernoulli theta. And so the way we express the idea of them being similar to each other is that they're like IID draws from the same distribution. That's a key idea in Bayesian modeling. In fact, I want to write that down here on this page. A straightforward way to make operational. I have tried to avoid the nasty verb operationalize. a straightforward way to make operational the idea, the judgment of exchangeability of unknown quantities theta 1 dot 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 down to theta k, let's say, is to regard them as IID draws, and it's really conditionally IID draws. Conditionally IID draws from the same distribution. EIST for short, e.g. theta I given mu and sigma squared are IID from the normal distribution with mean mu and sigma squared. That's an example, but that's not obviously the only distribution you could use, but it's an example. So key idea in Bayesian modeling, when you notice that your uncertainty about things is exchangeable, that will generally, in a parametric way to try to build models for the world, play out as treating them as like IID draws from the same distribution, and then you have to worry about what that distribution should be. So back over here on the PDF, our judgment of exchangeability of the theta i's translates into thinking of them as IID draws from a distribution. Why should it be the normal distribution? In fact, why should the distribution for the yi's be independently normal? Well, I have a good scientific case for the normal assumption here on that the third line of the model by the central limit theorem, by the Frequentis central limit theorem. Because each of the yi's, look at it, each of the yi's is the difference of two means, namely the means of a bunch of ones and zeros for whether people died or not. And each of those means is based on hundreds of observations. And the central limit theorem says those yi's just have to be normal. Because the sample sizes, they're the difference of two means. Each mean is based on hundreds or thousands of observations. They got to be normal. So the normal assumption at the bottom row of this model, I'm quite proud of. I'm very happy with that just fine. This one, I'm not proud of at all. This one is a conventional assumption, just pulled off the shelf because we find it useful and generally fairly easy to work with normal distributions. Later on with this data set, I will criticize that assumption and try to put in something else. In particular, and in the spirit of what we've been doing fairly recently, if one of the 6 studies has a yi that's so different from the others, what would you think of as a possible distribution for the theta i's? Take them as a t again and try to learn the degrees of freedom from it. It's going to turn out, interestingly, that when we do that, and I'll show you the analysis later, the data will reply that this particular data set with only 6 studies does not provide enough information in the data to allow you to learn what the degrees of freedom are in that T. And the way that plays out in the Bayesian story is interesting. How would it show up in Bayes' theorem for the data to be telling you that the data have no information about the thing you're interested in? That's right. If my posterior is about the same as my prior, because the data having not much to say means the likelihood is flat, right? And if the likelihood is flat, look at Bayes' theorem, the posterior and the prior have to be pretty much the same. And so that's another thing to write down over here. Data have no info about some quantity leads directly to the idea that the likelihood is flat, which leads directly by a Bayes theorem to the posterior approximately equaling the prior for that quantity. And what we're going to find when we fit this is that when we try to put down a t on unknown degrees of freedom, the posterior on the degrees of freedom is the same as the prior. There's just no information in this data set for that. So this normality assumption here in the middle level of the hierarchical model is conventional, But if we actually try to do better than this with only 6 studies, the data will thumpingly reject our attempt, so to speak, by pointing out that there isn't enough information in the data to fit the richer model anyway. So we might as well go with this because it's the most we can hope to learn from the data. And of course, now we have a model where there are 2 free parameters. We've now explained the theta i's in terms of this normal distribution, but now the mu and the sigma squared in this model, in the second level model, are unknown, so we have to put a prior on them. So the top level of this hierarchical model is a prior. Oh, I'm sorry. The top level of the prior, the top level of the model is a prior on the mu and the sigma squared. So it started out being 6 y sub i's and 6 thetas, which was impossible to estimate. But now we tell a story in which the thetas are IID from the same distribution, namely the normal with unknown mean and variance. So now we have 6 studies and only 2 unknown things about those studies. And so now we can fit the model, and we do so. We put a prior on mu and sigma squared, and we go from there. And the frequentist version of this story would be the same, except you wouldn't put the prior layer on. And that turns out to be a bad idea because there's something important we have to do in the prior to make sure that things behave well. So everything I've said in the last few minutes is basically down here in the next page or so. In meta-analyses of data like these, the VIs are typically known or assumed to be taken to be known because there's so much data. The middle level is where we bring in the study level covariates. Here there aren't any study level covariates. In effect, if you think about it, what would the linear model have looked like here? If there were covariates, we'd have said that theta I was related to the theta i's would no longer be identically distributed. They would be independent of each other, and the mean would differ according to some covariate x, for example. And this is like a regression model with no predictor variables. It's like a regression model with only the intercept term. So in effect, we're doing that. Yes, if you didn't have information, and by the way, and this is something that Chris mentioned in the break, notice how we're not attempting to model the data down at the level of the patients, which is scientifically a mistake if we have the patient level data available. You should never, as a statistician, frequentist or Bayesian, you should never aggregate the raw data unless you have a very good reason for doing so, namely that you're absolutely sure that your model is correct and the aggregation corresponds to reducing to the set of sufficient statistics in that model, and then you can go ahead and work with the reduced model based on the sufficient statistics. But in general, as an applied statistician, I have a powerful aversion to letting someone aggregate over the patients and give me a data set that's based only on the summaries at the study level. And as Chris pointed out over the break, when this stuff was done in the early 90s, it was impossible to get the raw data from people because they were not required to make it available to the journals as part of the publication process. And it was largely regarded as proprietary anyway, and so people didn't want to give it up. But these days, the better medical journals are now forcing people to make their data available in archives. So the New England Journal and JAMA and the other good journals, Medical Care, the other good journals now, say that you have to create de-identified versions of your data set to satisfy HIPAA compliance. You have to create de-identified versions of your data set and post them in the JAMA archive or the New England Journal archive. And that way other people can get your data for free and reanalyze it and maybe write a paper in which they say that they think your analysis is wrong. That puts people at greater risk of coming to incorrect scientific conclusions, but that's just what the scientific process wants, right? We want to know if somebody made a mistake in their analysis, and letting other people have access to your data is a good way to find that out. So these days, I would have been able to build a model down at the patient level, and I would have brought gender in as a potential covariate at the patient level. You're right. If all I have is study level summaries, then I could try to bring in a study level covariate like the percentage of females in the study, for instance. And that might be relevant because women might end up dying from a second heart attack or something like that at a different rate than men do. In fact, as you probably know, women have stronger constitutional, so to speak, from a health point of view than men do on average. women live longer than men do, and yet more men are born. The gender ratio is not 1-to-1 at birth. Did you know about this? There are rather more boys born than girls, and yet girls live longer. Have we talked about this before? What's the one thing? Yeah, the one thing that women do that men don't is they give birth to children, which is a big health insult to the body. And so you're right. If we had gender information here, that would be a study level covariate that we could bring in. None of those covariates were available in this meta-analysis. We just have the data in that little summary table. Okay, and so as I mentioned, why the error distribution should be Gaussian at this level of the hierarchical model is not clear. It's just a conventional option, and I will attempt to challenge it later. What is the meaning of these parameters, the mu and the sigma squared? I've told you what the theta i's mean and what the vi's mean. Mu is the big banana in this analysis. Mu is the overall effective aspirin on mortality. That's the thing we care about the most. We're wondering if that number, when we subtract placebo mortality minus heart attack mortality, we're wondering if that number mu is positive, and if it's large enough positive to be worth writing home about clinically. Sigma squared is another important parameter in this model. It represents between study heterogeneity, between study variability. And you can see right away that that's the parameter I was talking about before. If sigma squared were somehow 0, then what happens to a normal curve with a variance of 0? What does it collapse to? It's not a distribution anymore. It's like saying all of the theta i's are identically equal to mu. So if sigma squared was somehow known to be 0, that would be a model in which all the theta i's were pretended to be exactly equal to mu. And in that case, you can go ahead and pool the original data sets because everything is the same. So like it says here, if sigma squared were known somehow to be 0, all of the theta i's would have to be equal deterministically to that common value mu, and the resulting model would be simpler. It would go yi given mu are independently normal mu with different variances which we're pretending are known, and then you put a prior on mu. That's called a fixed effects meta-analysis. And the model we're working with now is called a random effects meta-analysis because the effect of study I is treated like a draw from a random draw from a distribution in this model. It's as though the theta i's are like random variables. And so they're called random effects in this model. Another name for them is latent variables because they are unobserved. The word latent in data analysis always means unobserved. So they are called random effects, also known as latent variables. And naturally enough, we'll talk about the random effects Poisson regression case study later. Naturally enough, as I said before, you can demonstrate by any of a variety of means that when the fixed effects model is a special case of the random effects model, the best thing to do from a Bayesian point of view is to fit the bigger model first, and then look and see what the evidence is in the bigger model for whether you can specialize down to the smaller one. And so what we're going to do is we're going to look really carefully at the Pasteur distribution on sigma squared. And if it puts a lot of its mass near 0, then that's the Bayesian modeling's way of telling you that the fixed effects model might be okay, and that the simple pooling would work fine. But if it puts all of its mass well away from 0, that's a very strong way of telling you that that there's no need to it's not appropriate to go to the fixed effects model. People used to do, back in the 80s and 90s, they used to do something that's analogous to what economists used for a while, a method called testimators that actually has been very badly discredited. In a situation like this, what you would do first is you would do a null hypothesis of the hypothesis test of the null hypothesis that sigma squared was 0, and only if the null hypothesis rejected would you go on and fit the random effects model. Otherwise, you would go with the fixed effects model. That turns out to be a very bad way to analyze the data because the operating characteristics of the hypothesis test get mixed up with the answer that you're interested in, and they get mixed up in a way that gives you wrong answers more often than you think. So that testimator approach, testimator comes from first doing a test and then doing estimation based on how the test came out. That's been deeply discredited, and all the testimator stuff that used to be done in economics is now done with hierarchical models. So they've gotten the word. Okay, well, you can fit this model with Bayesian methods, and we're about to in WinBugs. But I want to tell you about the maximum likelihood approach to fitting a model like this first, because it's quite revealing in an interesting way. And in any case, the maximum likelihood estimates often serve as very good starting values for our MCMC. So what's the maximum likelihood story? Well, on the way to that story, I'll tell you something that really surprised people when they first noticed it. Some algebra based on that model gives the following, that the conditional distributions of the study level effects theta I, given the data and temporarily pretending you know what mu and sigma squared are, so it's a kind of a full conditional sort of thing, sort of a Gibbs sampling full conditional thing, those distributions have a simple form that's highly revealing, and I'll show you this fact later on. So look at equation 2. It says the theta i's, if you knew the data values y sub I, and you knew the mu, and you knew the sigma squared, turn out in this model to be independently normally distributed, each with its own mean theta I star, and each with its own variance vi times 1 minus bi. And now look at the form of the theta I stars. It says some number times yi plus some other number times mu. And what's the relationship between the number in front of the yi and the number in front of the mu? 1 minus bi on the one hand and bi on the other hand. The bi's turn out to be numbers between 0 and 1. And so those two things, 1 minus bi and bi, do what simple thing? They add up to 1, meaning that this theta I star is a weighted average. That's right. And so what's happening is the conditional mean of the effect for study I, given the data and the mu and the sigma squared, is a weighted average of the sample mean for that study and the overall mean mu. And the amount of weight each one gets has a simple and also revealing form. The weights b sub I are given by the so-called, these b sub i's are called shrinkage factors, and they're formed by the equation, rather the second expression in equation 3. You take the variance of the outcome at the study level, v sub I, and you see how big that is compared with the total variance, namely the v sub I plus the sigma squared between studies. So it's kind of like an analysis of variance where the denominator has the between variation and the within variation, and the numerator just has the within variation. Now let's look at that for a minute. Suppose sigma squared were quite small. Then the bi's would be close to what? 1. And the weighted average would be mostly equal to what? Mu. And so what that says, and let's see if it's sensible, if there's hardly any between study variability, then you should estimate all the theta I stars to be mu. You should just pool all the data and stick it in one common pile, which makes perfect sense. At the other extreme, suppose that sigma squared was really big. There was a lot of between study heterogeneity. Then the bi's would be close to 0, and we give almost no weight to the overall mean, and we give almost all the weight to the mean in that study. That, again, makes very good sense. The first person to notice this was actually a frequentist, and his name was Herb Robbins, and he noticed it back in the 1950s. And it led to some startling mathematics done from the frequentist point of view by a prominent frequentist statistician at Stanford named Charles Stein. And so this is often referred since then to the Stein effect as well. What it says is, and this was a big shock to frequentists, is that to see what's going on in study I, you can get a better answer than looking only at the data in study I. You can get a better answer by taking a weighted average of the answer in study I and the overall answer for all the studies. And boy, was that a shock to frequentists when it first came out, because before then, no one had ever noticed any situation where that was a better thing to do. You should always just use the data in study I to estimate what's going on in study I, right? But remember what the model says. The model says the studies are similar. And so no wonder you get a better estimate when you take a weighted average. Because the model itself says you ought to take a weighted average because the things are similar. You said so yourself in the model. Therefore, no wonder you should be saying take a weighted average of those two things. And in this cool way, the amount of weight you give to the so-called grand mean mu versus the local mean in the data yi depends completely on how variable the studies are, just exactly as it should be to tell you how much pooling to do. So this is a way to do adaptive pooling, is the point. You're combining information across these groups in a way that's adaptive based upon how similar or dissimilar they are. It's a very cool thing in which the right thing happens automatically. Okay, another name for this is shrinkage estimation. Because what's happening is, since these weights are numbers between 0 and 1, therefore, of course, less than 1, each of the individual y sub i's are going to be pulled toward the grand mean by an amount that's greater or larger depending on this number sigma squared. And so these are called shrinkage factors, and then the resulting theta I stars are called shrinkage estimates. And what's happening is that unusually high or low individual studies get drawn back toward the overall mean or shrunken toward the overall mean in that weighted average calculation. When John Tukey first saw this in the 1950s, he referred to the process as borrowing strength, and it's a good name for it. In effect, what we're doing is we're using information from all the studies to strengthen our understanding of what's going on in study I. Yes? Yes, it is similar to that, except if you do that naively and you simply do something that acts like pooling all the previous studies, your prior will be very informative, and it'll correspond to that wrong mistake over there of just tossing all the previous studies together into one big data set. So what you really need to do is to combine all those previous studies hierarchically using this structure, and that will create the posterior from that becomes the prior for this study. But while you're doing that, why not just build a big hierarchical model with all of them? So, no, you're exactly right. Tukey made fun of this approach under some conditions. He was worried that people might try to combine things that ought not to be combined. And certainly, if you try to put things together that aren't very similar, this method can make you think that you're doing better even when you aren't doing any better, because sigma squared may not come out as big as it really is just because of sampling variability, and you'll end up thinking that you should do more pooling than you should. So when this method works well, Tukey referred to it as borrowing strength. When it doesn't work well, he referred to it as spreading weakness. And that also reflected his ambivalence. He was never very happy with the Bayesian story, and this narrative unfolds most naturally in the Bayesian story.
Bayesians realize this?
Right after Herb Robbins pointed it out, some smart Bayesian, I forget who, in the 50s said, "Oh, that's interesting. He's just doing something approximate Bayes in a hierarchical model. We can maybe do it better than that," and it went from there. The main papers on hierarchical models, the main paper that really broke open the floodgates was by my old friend Dennis Lindley and Adrian Smith, and that was about 1972. So it took a while for this to percolate into the Bayesian community, but it was right there. Now it turns out that in this model, you'd be interested in things like the posterior for mu given the whole data set, and you'd be interested also in the posterior for each of the study level effects given the data set. And it turns out that there aren't any conjugate priors. There are no closed form expressions. Even in this simple model here, where you've got Gaussian, there's no choice there's no way to choose a conjugate prior that makes those posteriors exist in closed form. So we have to use MCMC, and we will be doing so in a few minutes. But first, let's look and see how the maximum likelihood story goes. So if you were a likely hoodlum, one of these people who focuses only on likelihood, have I mentioned that term before? After Fisher, while Fisher was alive and then after Fisher died, there developed a camp of his followers, and they focused mainly for some reason at the University of Waterloo in Canada. There was a guy called Sprott, and I'm forgetting the other guys' names, and they tried to hold the Fisherian candle aloft for decades after Fisher died to try to create better and better likelihood inferences without writing down priors. A friend of mine who went to Waterloo and studied statistics there, he's the one who referred to them as likelihoodlums, and I like that term a lot. So if you are a likelihoodlum in this problem, for you, the only unknown parameters are mu and sigma squared. So you want to be able to write down the sampling distribution for y given only mu and sigma squared, and then make it into a likelihood by thinking of it as a function of mu and sigma squared for fixed y, right? That's the standard thing to do. But look, it looks not that pleasant, because to get to mu and sigma squared, to make a link between mu and sigma squared and y, you have to remove the theta i's, which sit intermediately between them. Oh, and someone asked for the graph for this, so let's look at the graph, because this helps to show how these models are fit so well by thinking about them in a Bayesian way. So first we have to have, thank you, graphical representation of model 1, page, what is that, page 4? Page 4 of part 4 of the PDF notes. Well, we're going to have a plate, what they call it, a series of these little sheets of paper, right? And the looping index, let's use I equals 1 down to 6, for example. And we can give 6 a name. I forget what I call it later on. I'm not blocking you from anything you need to know here. I'm just going to go back to this and see what I called it. I might call it K, which is an unfortunate choice given that we've been trying to use, yeah, I did call it K. We've been trying to use K to stand for the dimensionality of the parameter vector. Okay, and so each of these sheets is supposed to represent what's going on in one particular study. So there's one sheet or plate for each study. And now I'm going to look at the model and make sure I write down the right graphical model that goes along with it. Maybe I'll reproduce it here for you. Mu and sigma squared are draws from the prior. And then the theta i's given mu and sigma squared are IID draws from normal with mean mu and sigma squared. And then the yi's given the theta i's are independently normal with mean theta I and variance vi. So that's the model. So the data, anything indexed by I, obviously has to sit inside the plate or sheet for study I. And I'm going to put the yi's, unlike what they did in Doodlebugs, I'm going to put the yi's in square to denote known values. So things that are in square are known quantities, and things that are in circles are unknown quantities. Now, I have to put the theta i's in this plate I, because they vary from study to study, and they're unknown, and they have a direct causal relationship to the y's, because all you need to know to simulate a y is to be told the theta, and then you make a draw. We're pretending the vi's are known, remember? So all you need to know to be able to simulate the yi is to get the theta I. So the causal link in the graph goes directly like that. And what does the rest of the graph say? We have to have a mu and a sigma squared, and they have to sit outside the looping process. So there's going to be a stochastic node for mu out here, and a stochastic node for sigma squared out here. And the way you would get a theta I is if you had to know those, then you'd simulate that from draws from a normal distribution. So mu and sigma squared are both causal of the theta. And that's your graph for this model.
V.
What's that?
V
we're pretending are known. And so they're just numbers we don't have to put in the graph anywhere. I didn't have to tell you what the distribution was. This graph does not actually say what the distributions are. It doesn't say what the prior on mu is and what the prior on sigma squared is. It just says that that's how they're related to each other in a kind of causal fashion. Nodes that that determine other nodes are called parents, and the nodes that are determined by those parents are called children, from the obvious use of that language. And so at the top level, we have mu and sigma squared as parent nodes, and they're parents of the theta i's. And then the theta i's, in turn, are parents of the y i's. And that defines the graph. But look what happens. If you were to try to write this out fully, then you would probably, if you wanted to, for example, write down the joint distribution of all of these things before any data were arrived at, you'd have to have mu and sigma squared and all the theta i's. Actually, I'm going to call it the vector theta and the vector y. And so theta is the vector theta 1 through theta k, and y is the vector y1 through yk. You'd have to know all those things, so you'd be interested in the joint distribution of all those things. And now watch what happens. I would try to build that up by the usual rules of the product rule, because this says the joint behavior of mu and sigma squared and theta and y. The commas act like the word and, as usual. And so what I would do is I would write down, for example, p of mu, then p of sigma squared given mu, but the given part goes away if I'm prepared to write down a prior in which they're independent of each other in the prior, so that part there would go away. Then I would have to write p of theta given mu and sigma squared. Always, you know how the product rule works, always chaining along on the things that you previously were working with. And then finally, I'd have to write down p of y given theta and mu and sigma squared. So that's how it would have to look. But check out what happens with this particular hierarchical structure. The p mu is fine, the p sigma squared is fine, the p theta given mu and sigma squared is fine, but look what happens. The y i's, to get at them, you don't have to know the mu and the sigma squared. All you have to know is the thetas. And so what people say is that that yi and the mu and the sigma squared are conditionally independent of each other given the thetas. There's no information in the mu and the sigma squared. If I told you what the theta was, it's just like that thing we talked about before with the predictive distributions. If I offered you all of mu and sigma squared and the thetas to try to sample from the y's, you would politely say, I don't need to know the mu and the sigma squared. And so that's what makes these graphical models simpler. When you chain them along in this way, you discover that the hierarchies are set up in such a way that various things that you would have to put in there go away because of the conditional independences that are present in the graph. So y and the vector mu and sigma squared are conditionally independent given the theta i's. Conditionally independent given the theta vector. And that fact, which is embodied in the graphical model, allows for strong simplifications in this story. All right, so anyway, if you were a likelihoodlum, what you'd have to do in this model is you'd have to write down the sampling distribution of y given mu and sigma squared. You would have to get rid of the theta somehow. And the way that's done is the standard way you would try to do it, thinking from a Bayesian point of view. You would average over them, right? To get rid of something, you marginalize over it. And so you would need to somehow integrate out, is the phrase people use. You need to somehow integrate out the random effects. And you can do that in closed form in this model because the theta i's act like mixing variables. You're mixing across the random effects. And the normal mixture of normal distributions is, again, another normal, it turns out, when you look at the way the normal curves work. So if you set that mixture up in the right way and look at it, the normal mixture of normals is another normal. And so the likelihoodlums are able to work with this model pretty directly because they can integrate out the random effects, and I'll show you details on that later on. And they get the following likelihood function, which is equation 4 on page, whatever that is, on page 7 of the part 4 notes. And that's not very pretty to look at. The usual thing, of course, at this point, if we were doing the likelihood story, would be to take the logarithm of that, which would make it prettier, clearly, because it's a whole bunch of products that would turn into sums. Then you would take the first partial of that with respect to mu, and the first partial of that with respect to sigma or sigma squared, and you try to set those equations equal to 0 and solve them, and you discover that they have no analytic solution. So this is our first example of something that happens all the time in the likelihood story, in which, unlike the simple examples we've looked at so far, when you write down the set of, in this case, 2 equations and 2 unknowns that are based on taking the first partial derivatives of the log likelihood function with respect to mu and sigma squared, and you try to set them both equal to 0 and solve simultaneously, there is no closed form expression. So what you have to do instead is some kind of numerical solution of those equations. And in fact, those equations themselves suggest the following iterative scheme, which is based upon equations 5 and 6. Start with sigma hat squared equal to 0. That's the starting value for this iterative algorithm. Then look at equation 6. Put that sigma hat squared into that expression for wi hat, and that becomes a known value now because the vi's are known. So you get what are called provisional weights. It's going to turn out that the maximum likelihood estimate of the overall grand mean, mu hat, as you see in expression 5, is a weighted average of the individual means in each of the different studies weighted by these weights that we're about to work out. So start with sigma hat squared equals 0. That means that initially wi is just 1 over vi. Stick those wi hats in here, get a mu hat. Now go over here, stick that mu hat in here with the same w's you had a minute ago, and you know the v's, and solve that little guy there to get a new sigma hat squared. And now go around again. Take that sigma hat squared, stick it in down here, get some new w's, gives you a new mu, go back, get some new sigma hat squareds, then go around until it converges. Now, embarrassingly for the likelihood of them, sigma hat squared can converge to a negative value. And this is actually not a violation of the range possibilities for maximum likelihood. It turns out that likelihood methods and Bayes methods always have the property that it's never possible for the parameter estimates to fall outside of the boundaries of where the parameter has to live. Sigma squared has to be a positive number. It just happens as an unpleasant side effect of this iterative process that when there isn't much between study variability, sigma hat squared can converge to a negative value in this algorithm, in which case we simply remove embarrassment by setting it equal to 0. And so that would correspond to the maximum likelihood approach, claiming that the fixed effects approach is fine. And now we just iterate to convergence. And having done that, once you're done, the MLEs for theta I and BI are the obvious things to do. You take those shrinkage equations I showed you before and just stick in the MLEs for all the stuff in them that's unknown. These are called empirical Bayes estimates. They're not only maximum likelihood estimates, but they're also empirical Bayes estimates. And the reason is that if you look at what just happened, it corresponds to a Bayesian analysis in which you are allowed to cheat and use the data to specify the prior distribution as well as the likelihood function, and then use Bayes' theorem to get the posterior. And of course, we know that that's not right because you've used the data twice, once in the likelihood function and once in the prior. But under some conditions, the degree of usage of the data in the prior is relatively minor, is relatively modest. And these so-called maximum likelihood empirical Bayes estimates, MLEB estimates, or some people just call them EB estimates for short, or just ML estimates for short, these things can sometimes provide decent approximations to a full Bayesian analysis. But sometimes they don't. And when they don't, they always make a mistake in the direction of understating how much uncertainty you have because you've cheated, right? You used the data twice. And anytime you do that, your real uncertainty is bigger than you think. And so you'll come away from your analysis with uncertainty bands that are narrower than they should be, and that's never a good thing to do. So I'm not going to focus much on this MLEB thing in this class because we are so close to being able to just run a full Bayes analysis on this model in WinBugs, and why do we need this? But I will show you how it works. I have wrote a little R code to do it, and we can run that code and see what happens.
The way that you know that it went badly is the sigma squared.
If the sigma hat squared value converges to a negative value in the algorithm, or if the algorithm seems to diverge because the sigma hat squared value tries to go further and further negative, for example. Eventually, you can see that very bad things could happen if sigma hat squared can go negative. Look at equation 6. We could end up with zero weights. We could end up with we could end up with negative weights. We could end up with weights that were infinite, in which VI was equal to minus sigma hat squared, and we're dividing by zero. So very nasty things could happen with this algorithm. But in nice problems like this one here with the aspirin data, nothing bad happens. A prominent empirical Bayes guy is this guy Carl Morris, and he worked out some things. First thing he did is he worked out large sample approximations to the repeated sampling distributions of the MLEs, and they are given by the tooth parts of equation 8. It turns out that in repeated sampling, the maximum likelihood estimate of the overall grand mean mu, namely mu hat, is approximately normal, centered at the truth, and with a variance given by that expression, an estimated variance given by that expression you see there. And the theta I hats are approximately normal, centered at the truth, with the variance expression given by what you see there in equation 8. However, Carl Morris also showed that both of those variances in equation 8 underestimate how much uncertainty you actually have, because you have pretended you knew stuff in the prior when you were supposed to get the prior information external to the data set. And so they underestimate the actual sampling variances, and in fact, Morris has worked out some small sample adjustments, and you could read about it in one of his papers, which is cited at the end of this block. So here's some simple R code. It's not a sophisticated program. It takes in the data vector y and the vector of variances v, and it takes in a number lowercase m, which governs how many iterations you want the algorithm to do. And instead of actually checking for convergence, the algorithm just goes for the m iterations you ask for and stops. And it prints out various things on the way. So I could have fancified this by making it stop only when it's converged to when the difference between, for example, when the difference between the mu this time and the mu last time, the mu hat last time is smaller than some specified number. But it takes only 18 iterations to get convergence to 4-digit accuracy. And I put this program on the web page for the course. So let's actually run it and see how things go. So here under the aspirin meta-analysis data set, I have some R code for the maximum likelihood empirical Bayes story. So let me grab this code and show you what we get. I'll open a new R window. Let me first show you what I did to do this. So the first part is just exactly that function you saw before. Now I want to read in the Y data, and that's those same values from the table I showed you before, the actual estimated effects for each of the studies written on the percentage point scale rather than the decimal scale. And it's going to turn out, when we fit things in WinBugs, that I had already calculated the precisions for each of those normal data sets, which you recall are 1 over the variances. And that's part of a WinBugs file I'll show you after our next break. So I just took that code there and defined the v's to be 1 over the tau.y values. And now I've got the y defined and the v defined, and I just set m equal to 15 to show what happens. And here we go. In fact, I guess I'll set it equal to 18 here, because apparently when I wrote that PDF, I said you get 4-digit accuracy with 18 iterations. So let's go ahead now. I'm going to run MLEB with its arguments y and v and m. Isn't that the order in which I said they were in there? Y and v and m. And now I get a whole bunch of output instantaneously. And what the output looks like is the following. First, what you get, if you look at what I asked the function to do in the print commands, it prints the iteration number I as I runs from 1 to m, the current value of theta, which is actually called mu in our notes. So watch out. That's the thing that we're interested in, the grand mean. Then it prints out the estimated standard error for theta that you get from those Carl Morris formulas. That would be act like the frequentist standard error for mu. Then it prints out the current MLE estimate of sigma squared. and then it prints out in a little table right below that the W's, the current estimated weights, then the estimated weights normalized to sum to 1, then the estimated shrinkage factors, then the Y values, and then the estimated effects, those shrinkage effects, and then the standard errors for those shrinkage effects. So all that stuff gets done. And so when we start out, we think that that the treatment effect is not that big. And what happens immediately as soon as we iterate once is that the treatment effect jumps up to being quite a large number. It jumps from about 0.97 percentage points of improvement in mortality up to about 1.5. And then you'll notice in iteration 3, it drops down again to about 1.36. Then it goes up again to about 1.48. So you can see the convergence is not from below on mu. It's not from above either. It's a kind of seesaw convergence in which each iteration is either overshooting or undershooting the actual value. So then it goes down to 1.42 roughly, up to 1.46, down to 1.44, up to 1.45. Now we're down pretty well. We know we've got the 1.44 part pretty well nailed down. And now we're just mumbling about what comes after that. And eventually, after 18 iterations, apparently, we get that it has been 1.446 something for a while now, and it's now 1.4469 versus 1.4468. And so we actually have 5 significant digits pretty well pinned down. So on the basis of the maximum likelihood empirical Bayes analysis, we think aspirin improves things overall by about 1.4 percentage points with an uncertainty band driven by a standard error of about 0.8 percentage points. And we estimate that the between study heterogeneity on the sigma squared scale is about 1.5 percentage points squared, and so the square root of that is about 1.2 or 1.25, roughly, I guess 1.2 roughly. And so that means that we believe that there is quite a bit of heterogeneity between the studies on the order of more than 1 percentage point, and that's because that Amos study was so different from all the other ones. And in the maximum likelihood empirical Bayes analysis, I guess I can go back to the table down here. Those are what we get out as our MLEBs, and the weights turn out to be as follows. The weights in the algorithm are not normalized, and so I just add them up and divide by their sum to make them normalized. And it's interesting to see that even though Amos had very much the lion's share of the data, and that therefore in a simple weighted average fashion, Amos would have an enormous impact on the answer. Its weight, if you talked about a weighted analysis of a fixed effects nature, its weight would be on the order of 40 to 45%. What's 22 over 55? Isn't it about 40%? What's that? Yeah, it's about 40%, right? So even though it would have gotten that much weight if you just did the naive pooling analysis, in fact, that drops down to only about 0.28 because of the between study heterogeneity. The model is automatically saying to you that Amos's results should be downweighted because they're so different from the other 5. And it provides a principled way for figuring out how to downweight the results that are substantially different from the others. The actual data values in each study are given by the YI column, and these are the shrunken estimates of the true study level effects. Each of those numbers, the grand mean is about 1.45. If you look at it for a minute, you'll see that each of the theta I hats is intermediate between the YI value and the 1.45 value, just like the weighted average thing said. And so these things are being shrunken back toward the grand mean by varying amounts depending upon how big the shrinkage factors are. So the first study is being shrunk 64% of the way back to the grand mean. Amos is only being shrunk about 35%, but that's still enough, look, to take its estimated, its raw effect and shrink it almost all the way back into the positive territory. So it's being very heavily downweighted based upon the exchangeability judgment that we made, and that makes very good scientific sense. And I see that it is once again time for, in this case, our last break for the day. So we'll break for 15 minutes and finish things up at 4 o'clock.